In 1980, the United States attempted a high-stakes rescue of 52 American embassy staff held hostage in Tehran. The mission, known as Operation Eagle Claw, ended in a devastating failure at a staging area deep in the Iranian desert. The military relied on RH-53D heavy-lift helicopters for the extraction, but these machines faced rigid physical limits. They lacked the speed to move rapidly across vast distances and the operational reliability to survive the mechanical stress of deep desert sandstorms. To prevent another Eagle Claw, the Pentagon sought a machine that could hover and land vertically like a helicopter, but transit thousands of miles with the speed and efficiency of a turboprop airplane. In 1981, the Department of Defense launched the Joint Service Vertical Takeoff Landing Experimental Program. They tasked a partnership between Bell Helicopter and Boeing to turn a radical concept, a production tiltrotor aircraft, into a working reality. The Osprey was a departure from standard, iterative aircraft design. It was a high-risk effort to bridge a strategic gap, aiming to combine two disparate flight modes into a single operational airframe that could respond to global crises. The V-22's hybrid performance is driven by its wingtip nacelles. These pods house the engines and can rotate 90 degrees in exactly 12 seconds, shifting the 38-foot prop rotors from a vertical helicopter lift position to a forward-facing airplane configuration. Generating vertical lift for a 50,000-pound aircraft requires immense power. The Osprey utilizes dual Rolls-Royce AE1107C turboshaft engines, with each unit producing over 6,150 shaft horsepower. To survive engine failure, engineers developed the interconnect drive system. It uses drive shafts and a central gearbox to link the nacelles. If one engine fails, this system reroutes power across the airframe, allowing a single engine to drive both prop rotors for a safe landing. These systems enable the V-22 to carry 24 troops with a maximum vertical takeoff weight of 52,600 pounds. It maintains a service ceiling of 25,000 feet and reaches cruise speeds of up to 255 knots. By combining these specifications, the Osprey effectively doubled the speed and vastly extended the operational range of legacy helicopters, allowing for rapid insertions that were previously impossible without established airfields. Despite its theoretical advantages, the transition to active service was difficult. Following its 1989 first flight, the program struggled to pair a complex composite airframe with the new fly-by-wire flight controls necessary to stabilize a tiltrotor. These engineering hurdles came with a massive financial cost. The projected development budget, initially set at $2.5 billion in 1986, ballooned to nearly $30 billion by the end of the 1990s. This spending triggered political fallout. The Secretary of Defense repeatedly attempted to defund the Osprey, leading to a decade of uncertainty where the program faced constant threats of cancellation. The most significant setbacks were the fatal accidents. During the 1990s and 2000s, a series of major crashes resulted in dozens of casualties and repeatedly grounded the fleet, raising serious questions about the inherent safety of the tiltrotor design. The program survived because the military refused to lose the strategic advantage of tiltrotor speed. Planners maintained that the ability to reach a crisis point twice as fast as a helicopter outweighed the immense developmental and human toll. After 24 years of mechanical adjustments and safety redesigns, the Osprey finally achieved initial operational capability in 2007. The Marine Corps variant, the MV-22, now serves as the backbone of amphibious assault support, providing the rapid lift capacity needed to project power from assault ships. For long-range special operations, the Air Force utilizes the CV-22. This variant is explicitly tailored for the insertion and extraction of special forces in high-threat environments. The Navy recently adopted the CMV-22 variant for carrier onboard delivery. It handles the vital logistics and resupply missions required to keep a carrier strike group operational at sea. The platform is currently undergoing modern upgrades, such as the nacelle improvement program, to address lingering reliability issues. These modifications aim to extend the aircraft's operational life through the year 2050. The V-22's legacy is defined by its role in fulfilling the specific tactical needs identified decades ago. By surviving a multi-decade cycle of failure and redesign, it demonstrated that a single aircraft could reliably maintain both vertical lift and high-speed turboprop performance in active combat. Thanks for watching. If you found this technical history interesting, let us know in the comments which aircraft we should break down next.